Hi, I'm Jake, and in this video presentation I will be talking about an R package known as Seeker. The acronym SECR, or Seeker, stands for Spatially Explicit Capture Recapture. This package, as you might have guessed, uses spatial capture-recapture data to estimate population density and abundance as they relate to individual animals' locations and movements on the landscape. Seeker uses two main parameters, G sub 0, which is the probability of encounter at the center of an animal's activity center, and sigma, a measure of decline in capture probability with distance, to make estimates of animals' activity centers or home range centers, and to estimate the area each animal is most likely to occupy on the landscape. Then, based on these activity center estimates, Seeker populates a predefined study area with probable activity centers in areas where bears have zero probability of being captured, i.e. in places beyond the effective range of the detectors, to create what is known as a state space. This state space is what is used to estimate density. Spatially explicit capture-recapture provides a more sound estimate of density than traditional mark recapture, based on measurable spatial data, and it is robust to edge effects as well as differences in individual capture probability. Seeker also allows us to model variations in density across the landscape with the addition of spatial covariates of density. This package was created by Dr. Murray Efford of Otago University in New Zealand. Most of the original package was based off of Efford's program density, and as such the file formats are very similar. Now I will preface this very introductory run-through of package Seeker with a warning. As with so many other packages, there are numerous right ways to enter data and numerous wrong ways to enter data, and there are also many options for the creation and manipulation of the object classes and methods found within this package. These options were created with the aim of giving the user the ability to put together a sound analysis, and as such, they are vast and sometimes complicated. That being said, if you decide to use this package for an analysis, you will need much more than just my 20-minute intro webinar in order to ensure a statistically and ecologically relevant analysis of your data. I cannot stress enough how important it is to make sure you understand what options you're choosing and why, so please do your homework and take the time to read the help files and the other documents regarding the workings and use of this package before turning in the results of any analyses you might run with it. Let's begin this lesson with a short introduction to the object classes you will find within the Seeker package. I'll start by pulling up the Seeker overview document posted by Murray Efford, and I'll explain the page that relates to the Seeker object classes. I'm going to break this page down into normal people speak. So Seeker defines a set of R classes and methods for data from detector arrays and models fitted to those data. This is just a hyper-intelligent way of saying Seeker takes data and makes it into R objects that it can then use to run models, the outputs of which are also R objects. The four main classes or types of R objects Seeker uses are known as traps, capt hist objects or capture history, mask, and seeker. A traps object can be any number of detectors, including hair snares, camera traps, live traps, count detectors, etc., etc. Here is a list of the various types of detectors which can be found in Efford's Seeker overview document. This class contains, but is not limited to, trap names and coordinates. It can also include activity data for each trap, in other words, whether the trap was being used or not during each capture event. A capture history object or capt hist object is what contains all of your capture event data. So here's an example of a short capture history. It's not yet formatted for entry into Seeker, but this is also found in the Seeker overview document. This class contains, but is not limited to, the session, for example, year 1 of a 3-year study, the animal ID, the occasion, for example, week 3 of 6, and the detector at which the animal was detected. This class can also contain individual covariates such as the sex of each animal. The format of data entered into this object class may vary depending on the nature of the detector array and the capture data. A mask is, to the best of my knowledge, not actually a raster map of habitat near the detectors as it says in the document, but actually a spatial points grid. In other words, a grid that is formed using some set of boundaries that we will use to define potentially suitable habitat within our study area. The grid can be made within Seeker using the make.captHist function, or it can be produced outside of Seeker in other packages or programs, then imported as a mask object class through the read.mask function. If habitat-related covariates are specified, in other words, spatial covariates of density, then each one of the points in that mask will then have data associated with its coordinates appended to it. There are multiple ways to do this. I will only briefly describe the method I used for my research. The Seeker object class is the output of the Seeker.fit function. In other words, it is the output of a model you specify within the function, given the trap layout and the capture history data. The following graphical representation gives you a basic rundown of the steps taken to run a Seeker analysis. A trap layout file and a capture file are used to make a capture history or captHist file, which may or may not be used to help construct a mask object. The mask object and the capture history object are then used as inputs for the Seeker.fit function, which is used to run a spatially explicit model. The output of this model is recorded in the Seeker object class. From there, you can do many different things to evaluate, interpret, and display the results of your model. I will try to go over a few of these options towards the end of the presentation if I have time. So the first thing we're going to do here is set up a new script file by hitting Ctrl-O or opening in the new file menu a new R script. The next thing that we need to do is access our Seeker package. Now if you don't have this installed and you're using RStudio, you can go to the packages menu and hit the install option and type in SECR. I'm going to go over to my packages window and either click the box or type library parentheses Seeker. So now that the Seeker package has been loaded, the first object I'm going to create is my trap file, and I'm going to do this by naming egtraps as an object with the function read.traps. I'll take my trap file, which is a text file, and import it. Now if I type in the command view with a capital V in parentheses my traps object egtraps, and then run that code, I get to view the traps object in the same window as I would my scripts. So next I'm going to read in my capture file. Code I use to do that is read.table, and once again I have a pre-made text file. This time I'm using header equals true because I will need the title to be there for the sex covariate so that I can specify it later in my models. Next I'm going to view my captures object so that I can verify that it is in the data format that I want it to be in. So once again I'll be using view and then in parentheses the object name egcaps. Looks pretty good. Session ID, occasion, trap, and sex are all properly entered. So my next step is to take the capture history object and the traps object and to put them into a combined capture history format. This is achieved through the make.captHist function. I'm going to pull it up now that I've pulled up the capture history object help file. This is how you construct a captHist object. There are, once again, many ways you can do it. I'm doing it in a method that I felt was simple enough for my data formats. In other words, since I had put them together into text format already, I thought it was easier to just load them as separate objects and then combine them within Seeker without any extra import steps. So here we go. I've got my capture object, traps object. The association between those two is the trap ID, and the covariate names are, in quotations, sex. That's why I needed the headers from earlier. Now I'm typing in verify my capture history object to make sure that there are no errors, like coordinates that don't exist for certain traps, and so on and so forth. And we had no errors found, so there's a little smiley face. So to get a more in-depth look at the structure of the capture history object, you do summary EGCH. That gives you your object class, your detector type, detector number, average spacing, the range of the file that is created, and the number of counts by occasion. Very useful data to check if anything might be missing or otherwise not right. So the next function I'd like to talk about, and the last regarding the capture history object, would be the plot capture history function. This allows you to have another graphical representation of your capture history. It gives you the occasions, detections, and the number of animals, and you get to see your trapping grid as it relates to your recaptures. And now we have the final preparatory step before we run our models. That is the make.mask function. This method allows you to construct a habitat masked object from your existing data, i.e. your trap file and your capture history file. And it is a relatively good method. In this code, I'm basically just using my traps from my capture history file and setting a 16-kilometer buffer around each and every trap, which is why you see the circles all over the study area. Now each dot represents one point on the spatial grid concept that I was talking about in the beginning of the presentation, and the spacing of those dots is determined automatically if you do not put in code to specify. Now what I'm doing right here is I'm putting spacing equal to 1,000 meters, so there will be a 1,000 meter gap between each point on that grid when I rerun this. Plot it again, and you see that the spacing is a lot closer. Originally what it was doing was determining your spacing based on the horizontal distance of the extent of your object, your mask object, based on the 16-kilometer buffer and all the traps that you had laid out. I like to specify my spacing because, first off, it gives me even spacing, consistent spacing across study areas if I have multiple study areas to contend with, and two, it allows me to specify a smaller scale and thus define a more fine scale spatial analysis of my data. Now say you have a better idea of what constitutes habitat and what constitutes non-habitat on your study area, and you've made a polygon in ArcMap or some other GIS software that allows you to differentiate between the two. In other words, you've made a polygon that shows only your habitat. It's cut out the non-habitat. Well, the makeMask function allows you to add in a polygon. But first we must import a polygon from an outside source. That requires the package map tools. So we have to install or open map tools, and then we use the read shape poly function within that package to import a spatial polygon into our global environment. So I plotted it. Looks good. This is a polygon that has removed major water bodies and cities from my original 16-kilometer buffer polygon, which I also created in ArcMap based on the same criteria that Seeker uses to make its trap buffers. So I've made a new mask object using the poly equals function within the make.mask function to specify my bounding polygon, and you can't see it very well, but some of those points have actually been erased around the major water bodies, and they've definitely been erased around the new boundaries. There's a comparison for you. So that function allows me to better define the habitat that exists within my study area. Now I must throw in a warning here. Depending on the spacing of your points within your grid and the complexity of your bounding polygon, it might take up a lot more computing power than you realize to make a mask using the make.mask function. That is one of the reasons why I turned over to the read.mask function, which just allows you to basically input a text file with a bunch of point coordinates and attached habitat covariates, as I'm showing you right here, into a mask object. It's a lot easier for me to just go into ArcMap and make a grid myself and then attach covariate data to it and then just import the whole thing using the read.mask function, as opposed to making a mask that might or might not take a long time to do and then having to add covariates from separate raster files. These are all of my covariates for my current analysis on the Florida black bear population. So now I've made a fourth mask using a text file that has coordinate data and covariate data attached to it, and as you can see, it looks pretty much the same as the previous mask. It just doesn't have a backdrop of a polygon with it, and it is essentially the same mask. It is a different kind of mask, but it displays more or less the same data. There might be some small differences based on the number of points that might have been taken off and the number of points that might have been generated in ArcMap versus R, but those differences are very, very small. I have tested them. So I pulled up a summary of my fourth test mask, and it shows all of my habitat covariates, my covariates of density. They're all there. They all seem to look good. Everything has been imported successfully. That was a lot easier, in my opinion. Took a lot less steps in R to append those data to a text file and then to just import them like that instead of using the add covariates function. However, I should probably show you guys that, so I might just do that next. So now I'm finally going to talk to you guys about the seeker.fit function. That is the function that allows you to run models based on the data you've entered. So what Seeker does with this function is it takes your capture history and your traps and the mask that you put together using the make mask or read mask functions, and it maximizes the likelihood of 3 parameters given the data that you gave it. Those parameters that I talked about in the beginning of this webinar: G sub 0, sigma, and ultimately density. Now, when it estimates those parameters, it's estimating them in a specific link. So you're getting beta estimates first, and then it back transforms them based on their link functions to the quote-unquote real parameter estimates of density and G0 and sigma. You can specify at this point any covariates that you might have added in to your capture history files or your trap files or even your mask files. The formulae that you use can be rather complicated, so it's really important that you read up on the help files that specify how to properly write these formulas so that you get a valid analysis from your data. So now I'm putting together my first model, and the only model I'm going to run for this webinar. It is essentially a null model. D, sigma, and G sub 0 are all modeled as a function of 1, which means there are no other covariates or other variables that are influencing their models. So this model should run fairly quick, and there it goes. Won't take too much longer here to complete. Once it has completed, I will simply type in the name of the model, and that will give me a full output of all the beta parameters. It'll give me a variance covariance matrix. It'll give me my real parameter estimates for density, G sub 0, and sigma. And then it'll give me, of course, all of my specs for my capture histories and my traps. Now you might be wondering, how do I get my estimate of population abundance? Because obviously you still should be able to do that even though your main goal is your density estimate, and you just have to use a different function in order to get there. The function is called region.n. It gives you an output of expected n or expected population size, and realized population size, which are described in more detail in some of Dr. Effort's publications. So region.n basically gives you the estimated abundances for the region, or more specifically for the area that you defined in your mask function. So there is one more thing that I would like to add before the end of this webinar, and that is the AIC function. But first, I need more than one model to compare, so I'm going to run my second model, which has G0 as being modeled as a function of B, which is a behavioral factor. Shouldn't take too long. Basically, it's a simpler way of saying that bear behavior influences your capture probability at the center of their activity center. Model's running. Model's still running. Sweet Jesus, the model is running. It'll keep running until the end of time, I do believe. Or maybe for a couple more iterations. Look at that, 35.81 seconds. Wow, these are simplistic models. Now that we have two models, one super simple and one not as simple, we can compare them using the AIC function. AIC, and then I just type in my models. I can do a lot more stuff with AIC, but I'm just going to type in model 01, model 02, and run it. It gives me an output. It'll give me my model, my detect function, my detection function, my number of parameters in each model, negative log likelihood, AIC, corrected AIC, which is corrected for a small sample size, which in this case we need because Eglin has a pretty dang small sample size, the difference in corrected AIC values, and the AIC weights. Now, interestingly enough, it looks like the first model, which is the null model, performs ever so slightly better, 2.53 AICC points better than the behavioral model, which is interesting. I didn't think it would be that way, but yeah. So that's one way to compare model fit. There are many different ways to analyze the data that you have in here. Look at the beta values and determine whether or not there is a strong influence of any of your variables on your models. Determine whether your models are even ecologically relevant in the first place before you start running them. Make sure that everything checks out. That being said, I still have a lot more to learn about this program before I can officially publish any of my results, so please, please, please do your homework. Thank you for watching, and have a very good day, or night, or whatever it might be.